Today we're digging into operational technology, OT. We're talking about that critical stuff, beneath the surface. The controllers for the power grid, pumps on pipelines, factory assembly lines. Our mission is to demystify securing all that. We want to give you the blueprint, the Purdue reference model, levels 0 through 5. We need to define those boundaries, understand the tension between IT and OT, and map out exactly how we bridge that gap safely without causing some kind of catastrophic failure.
Yeah, and having that map is, well, it's critical. Especially now, we're deep into IT-OT convergence. And when you merge these networks, huge business value, sure. Real-time visibility, predictive maintenance, all that good stuff. But, and this is the big but, you also massively expand your attack surface. It's a risk you have to manage deliberately, structurally. Or efficiency gains could cost you safety.
Okay, right. So let's unpack that convergence by looking at the fundamental split first. Because if someone just tried to slap standard IT security onto a factory floor, well, that could go sideways fast, couldn't it?
Oh, absolutely. Spectacularly wrong, yeah.
So what is the core difference, structurally, culturally, between IT and OT?
It really boils down to priorities, risk priorities.
In IT, we live by the CIA triad: confidentiality, integrity, availability, usually in that order. Keep the data secret. If your IT system goes down, okay, it's bad data loss, maybe a privacy breach, lost productivity, you lose some sales figures perhaps. Annoying, costly, but usually recoverable. In OT, though, it's flipped. The main goals are availability and process safety, then integrity, confidentiality. Often it's way down the list. If an OT system fails, the stakes are just so much higher. You're not worried about a spreadsheet. You're worried about equipment damage, people getting hurt, safety incidents, or the major environmental impact, pipeline explosion, chemical spill. That immediate physical threat changes everything about security decisions. That distinction is huge. Productivity loss versus physical safety. And it means you can't just push a patch to a controller like you do a server.
Exactly. Which brings us to the operational differences. The change cadence is completely different. IT, frequent patches, quick upgrades, that's normal. OT needs these carefully planned windows for changes, often tested on simulators first because unexpected downtime, just not acceptable. And the tech itself, it's often from different eras. You've got modern ERPs talking encrypted HTTPS versus, legacy PLCs, RTUs, SCADA systems, running old school protocols like Modbus, Profinet, DNP3, things designed for speed and isolated networks, not security.
Well, I was going to ask about those protocols, Modbus, DNP3. Why are they so much harder to secure than, say, HTTPS?
Well, it's because they were designed decades ago, really. For efficiency and speed inside what was assumed to be a physically secure, trusted, completely isolated network, they often lack basic security functions, like natively, no encryption, no authentication, sometimes not even basic error checking beyond simple parity. So unlike HTTPS, which checks identity and encrypts everything, if an attacker gets onto a Modbus network segment, they can often send commands, tell a pump to turn on, a valve to close, no password needed. The original assumption was always that physical locks were enough, that inherent fragility. That's why we need those specialized protocol-aware firewalls later.
Makes sense. That difference is precisely why the Purdue model is so valuable, right? It gives us that structure, that hierarchy, to apply the right controls in the right place. Let's walk through it. Level 0, ground floor.
Level 0, yeah. The reality layer. This is the actual physical process. The sensors measuring temperature, pressure, the motors, the valves, the actuators doing the work. This is where bits turn into action. So security here, it's almost entirely physical, protecting the wires from damage or tampering, ensuring signals are clean, dealing with heat, EMI, stuff like that. Think about it. If someone physically messes with a limit switch or cuts a sensor wire, all the fancy digital controls above it are suddenly blind or getting bad data.
Huh. That's interesting. So in a discussion about digital security, you're saying maybe the most crucial control at the very bottom is still just a locked cabinet or some shielded cable.
Often, yes.
Not all.
The digital security is only as good as the physical reality it's based on. But okay, moving up. Level 1. This is where the digital brain starts.
Tell us about level 1.
Level 1 is basic control. Here are your PLC's programmable logic controllers and your RTU's remote terminal units. They're executing the real-time control logic, taking level 0 inputs, making decisions in milliseconds. Security here has to be focused on hardening the device itself. Disable every unused service. Keep firmware updated, but carefully, and crucially, physically lock the programming ports.
Why is locking that port so important? Seems basic.
Because it's the ultimate backdoor. It offers the highest level of privilege. If someone can just walk up and plug in a laptop, they can download the logic, upload malware, change set points, completely bypassing any network security you have. You also start your network segmentation here, really aggressively isolating groups of PLCs, like cell by area, whatever makes sense for the process.
Okay, PLC level secured.
Yeah.
The level 2, the operator interface.
Level 2 is area supervisory. Think SCADA servers, HMIs, the human-machine interfaces. The operators use maybe engineering workstations. The security focus shifts a bit here. Role-based access becomes critical. Not everyone needs admin rights or access to engineering files. Strict application allow listing, too. Only approved software runs. And you need really tight control over who can make changes and detailed logs of what changes were made.
So if level 2 is about local area control and visibility, level 3 must be the plant-wide view just before we hit the corporate network.
Exactly right. Level 3 is site operations. This is where you find systems like the MES Manufacturing Execution System, batch management, the process historian databases logging all the data, site-wide scheduling. It's the central hub for the plant's operational data, the highest level of the, let's call it the true OT environment. And, this is key, the big firewall, the DMZ, sits right above this level.
Got it. Which puts level 4 firmly in the business realm.
Precisely. Level 4 is enterprise IT. Your ERP system, business analytics, staging servers, corporate reporting tools. It connects the business side to production. But, and this is non-negotiable, it should only talk to level 3 through services brokered in that DMZ. No direct connections allowed. Ever.
And level 5, that's the connection to the outside world, which seems to be getting bigger all the time.
Level 5 is cloud and external. Think IoT platforms sending data to the cloud, maybe OVM remote access for diagnostics, cloud-based analytics services. Security here, it's all about strong identity and access management, IAM. API gateways to shield your internal systems, encryption everywhere, and really strict rules for remote access. Time-boxed access is crucial. A vendor needs to check a machine. Okay, they get access for, say, 4 hours, it's logged. Then it's automatically shut off. No permanent VPN tunnels hanging open.
Okay, great map. Levels 0 through 5 laid out. Now, you've stressed segmentation and the DMZ. Let's focus on that bridge. Where exactly does this DMZ live architecturally, and what makes it more than just a firewall?
Right. The DMZ demilitarized zone sits squarely between level 3, site operations, and level 4, enterprise IT. Think of it as level 3.5. Its job is basically to be a strictly controlled broker and inspection point. No direct traffic between IT and OT is allowed, period. Everything has to pass through this checkpoint.
So it's not just filtering packets, it's actively managing the conversation. What kind of specific tools do you put in there?
Yeah, it's much more than a simple firewall. You need specialized gear. Industrial firewalls, yes, set to default deny, but crucially, they need to be protocol aware. They have to understand Modbus or OPC or DNP3 deep inside the packet, not just ports and IPs. And within that DMZ zone itself, you place things like dedicated jump hosts, reverse proxies, maybe application-level gateways, sometimes even data diodes for really critical stuff.
Okay, jump hosts, reverse proxies. Why are those better than just setting up some firewall rules?
It's about controlling who initiates the connection and how. The jump host is mainly for human access engineers, technicians. It forces them through a single audited point, usually with multi-factor authentication. It stops someone from, accidentally bridging networks with their laptop by connecting directly from the IT side into the OT side. They have to go through the jump host. The reverse proxy is more for machine-to-machine communication. It ensures that systems in level 4, the IT side, can't just reach into level 3 whenever they want. Level 3 systems might push data out via the proxy, or level 4 might request data through the proxy. It brokers the connection. It prevents direct inbound attacks from IT to OT systems.
And data diodes. That sounds physical.
It is physical. For extremely sensitive, one-way data flows, maybe sending critical safety data or production counts up to IT. A data diode provides absolute enforcement. It's literally hardware that only allows data to flow in one direction. Light signals one way, but no path back. It gives you physical assurance that nothing from the potentially less secure IT network can ever flow back down and interfere with the controls. It's the ultimate one-way street.
That level of control is serious. Okay,
Yeah.
so let's define those flows. What typically is allowed to go upward from OT to IT through that DMZ?
Upward flows are usually informational. Things like production KPIs, key performance indicators, quality control data, alarms and event logs from the SCADA system, maybe historian data being replicated up for analysis. This data is generally less risky for IT to consume as long as the services handling it in the DMZ are secure and properly configured. It's mostly read-only from the OT perspective.
And downward. From IT back into OT, that sounds much scarier.
It is much higher risk and needs extreme scrutiny. Downward flows have to be strictly limited and controlled. We're talking things like approved patches for HMIs or servers in level 3. Maybe deploying a new tested golden image for a workstation, or sending down new production recipes or batch parameters. These things must only happen during planned maintenance windows. They need thorough testing beforehand. You need rollback plans. Everything needs to be logged. You absolutely cannot allow anything that could be easily weaponized, like letting IT push down configuration changes automatically without intense oversight and process control.
Okay, zones defined, boundary built. Now, the really tricky part, keeping it secure day to day, especially when these industrial processes often can't stop. We hear zero trust everywhere in IT now. Can you really apply that mindset in OT?
Yes, you definitely can apply zero trust principles in OT, but you have to adapt them. The core idea is strong identity, segmentation, least privilege, assuming breach they still apply. But the implementation has to respect the absolute priority of availability and safety. So instead of constantly re-authenticating a user trying to access a PLC, which could disrupt timing, you might focus more on strong device identity. Is this specific HMI allowed to talk to this specific PLC? You verify a device posture. You apply patches, but only during those planned windows, not on the fly. The key is adapting. You cannot implement a security control, no matter how good it sounds in IT, if it introduces any risk of causing an unexpected process shutdown. That's the red line.
That need for zero impact brings us to visibility. If you can't actively scan these fragile systems, how do you see what's going on? How do you monitor for threats?
Passively, this is probably one of the highest leverage wins for OT security visibility. Avoid those active network scanners, the scan everything tools common in IT. Sending unexpected packets can easily crash legacy controllers or disrupt sensitive timing loops. They just weren't built for that kind of interrogation. The best approach is passive monitoring. Use network TAPs, test access points, or configure mirror ports on switches. You basically make a copy of the network traffic and analyze it offline. You just listen. You don't transmit anything onto the control network itself. This lets you discover assets, map communications, detect anomalies, see potential threats, all without risking the process. See everything, touch nothing.
Listen quietly, don't poke the bear. Makes total sense. Okay, let's tackle patching. The nightmare for every security team, but maybe even worse in OT. Since you can't just patch whenever, how do you do it with purpose?
Patching in OT is it's a formal event, a planned project almost. It absolutely must happen only during scheduled maintenance windows when the process can tolerate a brief outage or has redundancy. You have to test the patch first, rigorously, on a test bed, a simulator, maybe a digital twin if you have one. Make sure it doesn't break the application or cause instability. And before you even think about deploying to production, you need a documented, tested rollback plan. How do you undo this if it goes wrong? Preparation is absolutely everything. You can't afford to brick a system that takes hours or days to recover physically.
And if, despite all that, the worst happens, an attack gets through, or something fails catastrophically, what's the last line of defense?
Backups. Solid, reliable, tested backups. They're not just any backups. We're talking offline or immutable backups for your crown jewels in OT. That means PLC project files, the actual logic, historian databases, MES system configurations, engineering workstation images. This isn't just data, it's the intellectual property of how your plant runs. And the key word is tested. You have to actually try restoring from these backups regularly, quarterly, maybe even more often for critical systems, because if you haven't tested your restore process, you don't have a backup. You just have data stored somewhere, maybe.
That's a really crucial point. Untested backup equals hope, not a plan. Okay, as we wrap this up, let's hit some common mistakes, the big pitfalls people should look for right now in their own environments.
Number one, without a doubt, flat networks. If your IT and OT networks are sharing the same VLANs, even if they have different IP ranges, stop. Fix that immediately. That single flat network just bypasses all the Purdue levels, all the segmentation. It gives an attacker who fishes someone in accounting a potential highway straight to your controllers.
Ouch. Okay, what else?
Second big one, allowing direct connections from level 4 systems like ERP or business intelligence tools straight into level 3 or even level 2. Bypassing the DMZ entirely. If you see firewall rules allowing the ERP server to directly query a SCADA server, that's a huge red flag. You've defeated the whole purpose of the segmented architecture.
Makes sense. What about the human element?
Yes. The third one, engineering laptops. These things are often ticking time bombs. They frequently have internet access for updates or remote sessions, and they have powerful software with admin rights to program PLCs or configure HMIs deep in the OT network. That makes them a perfect mobile infection vector. Malware comes in via email, then hops onto the control network when the laptop connects. You need strict policies, maybe dedicated air-gapped laptops for OT work, or enforcing connection only through jump hosts.
Right, and the last one, connections we don't control.
Exactly.
Yeah.
Third-party remote access, those untracked vendor modems plugged directly into a control panel somewhere, or shared, never-changing credentials for remote support. Massive risk. You need to inventory all remote access points, force them through your DMZ architecture, implement strong, individual temporary credentials for every external user, log everything they do, get control over those connections.
This has been incredibly clarifying. We've mapped the terrain, built the boundaries. If you take just one thing away from this deep dive today, it should be this. Get that DMZ built between level 3 and level 4. Make sure it has proper inspection, uses allow listed rules, logs everything, and hunt down and eliminate any direct paths between your business network and your control network. That Purdue structure, especially the L3, L4 boundary, it really is the essential shortcut to understanding and improving your industrial network security.
Absolutely. And maybe a final thought to connect it all back. We started down at level 0, remember? The actual physical reality. The sensors, the wires, the actuators that make things happen. It raises an interesting question, doesn't it? Despite all these sophisticated digital security layers we've discussed, levels 1 through 5, firewalls, encryption, monitoring, how much does the ultimate safety and integrity of that whole industrial process still boil down to just good old-fashioned physical security? Managing who can touch the wires, ensuring signal quality, locking the cabinets, right there at level 0.
Something to definitely think about next time you're looking at a network diagram. Or maybe just checking the lock on that control panel door. Thank you for joining us for this deep dive.
Until next time.